end of the last lesson, I said that I would tell you all about why we do definite integrals in the next lesson, which is this one. So we're still doing definite integrals, but now we're going to be using them in a slightly more applied context. Now, you will remember from the last chapter that differentiation finds the gradient of a line. Well, integration finds the area under the curve. We can go into this in so much more detail, but not now. Take A-level maths. Or just come talk to me about it. Anyway, integration is going to find the area underneath the curve. And I'm not actually going to prove this to you now. Again, if you're interested and you want to see a proof and why this works, come and see me. It's quite nice. I'm just going to demonstrate to you that it does work. And I'm going to just give you one example of it working. I want you to trust me after that. Okay, so here is a nice easy one. It's easy because my line is straight. Okay, so this is my curve, even though it's straight. Y is equal to 2x plus 1. Okay, and that's that red line there. You can see it's got a y-intercept of 1 and it's got a gradient of 2. Bounded by x equals 2 and x equals 4. Now these are the vertical lines here. X is equal to 2 and x is equal to 4. I'm not sure you can see that down there. That's 2 and that one's 4. So what we're trying to do is find the area here. And of course that's the trapezium. And we know how to find the area of a trapezium even without me singing the song. So let's find the area of that trapezium. We've got two parallel sides here and we can read off what the lengths are. So that blue line here, the x equals 2 line, that goes from 0 up to 5. So the first parallel line has a length of 5. The second parallel line goes from 0 all the way up to 9. I think I need a new pen. Okay, so we've got two parallel sides, 5 and 9. And the distance between them is from 2 up to 4, so we've got a distance of 2. So we all know the area of a trapezium is equal to half the sum of the parallel sides times the distance between them. Times it by 2. So this gives us a half of 14, and then timesing it by 2, which of course just gives us 14. Okay, so the area under that curve is 14. Now we're going to do it the more advanced way, using integration. And check that it works. So what we want to do here, the equivalent to finding the area underneath that line, is to integrate the equation of the line with respect to x from 2 up to 4. So those were the lines that were bounding our region. So when we integrate it, we lose the integral sign, 2x squared over 2 plus x from 2 up to 4. Let's simplify that first. X squared plus x from 2 up to 4. Now let's substitute those in. So we're going to have 4 squared plus 4 minus, substitute in the 2 squared plus 2. 4 squared is 16, add on 4, we get 20. Minus 2 squared is 4, add on the 2, and we get 6. And take presto, we get our 14. Now, I've picked a really easy curve to demonstrate that this does work in two different ways. I could pick a curvy curve, like x squared or x to the power of 3, and if you're interested in seeing these two methods show the same result in what actually does constitute a proof, come and see me. But otherwise, I just want you to trust me that if you integrate a curve with respect to x between two limits of x, so from 2 on the x-axis up to 4 on the x-axis, you will get the area underneath that curve. And the reason that we integrate rather than using the trapezium rule is that it's much easier to do when you've got a curvy curve. So let's give you an example. And I'm going to pick, I believe, quite a difficult one. Okay, find the area between the curve this and the x-axis. Now you'll notice that they haven't given us limits. They haven't told us between x is equal to 2 and x is equal to 4, for example. What we need to do here is find it. Now, you can recognise here that we've got a graph shaped like an unhappy face. And what we would expect to happen is for some of that graph to be tracked so that we can find the area between this and the x-axis. I will draw a sketch in a moment once we've worked out where this graph exists. Now, if we're finding out where it crosses the x-axis, that is where, I'll just draw a random graph here, it's where we've got x coordinates but the y coordinate is equal to 0. So, get rid of our random graph so we don't confuse ourselves. It's where y is equal to 0. So I'm going to substitute in that y is equal to 0. And now I've got an equation where the only unknown is x. Therefore, I can find out what x is. I'm going to do that by factorising. And you'll notice that this is the difference of two squares. So we've got 2 plus x and 2 minus x. Therefore, each of these brackets has to be equal to 0. For this one, x is equal to negative 2, and for this one, x is equal to 2. Therefore, actually, my random graph wasn't too far away. I know that the shape of the graph is an unhappy face, and I now know that this point is at negative 2, and this point is at 2. And what they've asked me to do is find the area between the curve and the x-axis. And so that means that we are finding this area here. So what that means we need to do is integrate 4 minus x squared, so that's the curve with respect to x, between negative 2 and 2. So let's do that now. When we integrate it, we lose the integral sign and we've got our square bracket here. We're going to get 4x minus x to the power of 3 over 3. And we go from negative 2 up to 2. So just like before, we're going to substitute in the first limit here and then minus what we get when we substitute in the second limit. So let's substitute in x is equal to 2 first of all. So we're going to have 4 times by 2 minus 2 to the power of 3 all over 3. Minus from that, x is equal to negative 2. 4 multiplied by negative 2 minus negative 2 to the power of 3 over 3. Okay, 4 times by 2 is 8. Minus 2 to the power of 3 is 8 divided by 3, and I'm just going to write that as 8 over 3 for now. Minus from that, 4 times by negative 2 is negative 8. Minus, well, it's a minus, but when I do negative 2 to the power of 3, negative 2 times negative 2 times negative 2, that gives me negative 8 over 3. I'm going to sort this out a little bit more. Here, we've got 8 minus 8 over 3. Now, minus 8 gives me plus 8. Right, we've got minus, so this is now a positive, but there's a minus here, so it is actually going to be minus the 8 over 3. And you can see here that we can probably add this up quite nicely. 8 plus 8 is 16. Minus 8 over 3 minus another 8 over 3 gives us minus 16 over 3. Okay, and we can leave it like that if we like. And again, I'm going to be relatively lazy because I can. 16 minus 16 divided by 3, I can get that as 32 over 3. And that is the area that I've shaded here in red. So it's the area underneath this curve. Okay, There we go. So it's your turn again. Right. I want you to sketch this curve first of all, nice and easy. Just for x's between -3 and 3. Second of all, I want you to shade the area bounded by the curve, these two lines and the x-axis. And then third of all, we need to find, by integration, the area of the shaded region. Okay? Put this on pause, have a go, and then check that you've done the right thing. Okay, sketch the curve. Well, we can all do that, nice and easy. Do it over here. It's just a smiley face graph. Okay? Shade the area bounded by the curve, the lines. X is -1, so that's going to be here. -1. And 2, so a little bit further along, 2. And the x-axis. So the area that we're going to be finding is a little bit of this one, and that bigger region there. Okay, now the slightly more difficult bit. Find by integration the area of the shaded region. So let's set up the problem first. We want to find the area of the shaded region, so that's going to be integrate x squared with respect to x between -1 and 2. So we're going to do the integral first, get rid of the integral sign once we've done the integration, x to the power of 3 over 3, from -1 up to 2. Substitute in 2 to the power of 3 over 3 minus -1 to the power of 3 over 3. Let's sort out what this gives us. 2 to the power of 3 is 8, still divided by 3, minus, okay, let's be careful here, -1 to the power of 3. So -1 times -1 times -1 is still a negative. So that's going to give us 8 over 3 plus 1 over 3, which is equal to 9 over 3, which of course is equal to 3. So the area underneath this curve is just 3. Nice and simple. And that is the end of lesson